Chemical Kinetics, Chapter Introduction. In this video, we'll just quickly be going over kinetics and the reasons for it and some basic principles that you probably already know and just relating them into chemistry. So first off, let's talk about rates of reactions in terms of just fast or slow. So we'll talk about it very conceptually first. So for instance, we have certain reactions that we can think of as being fast right away. For instance, combustion. Your previous classes have talked about this specifically quite a bit, so here I just want to point out that it's something that we've seen as pretty fast in relation to our own personal timescales. So the next one that we'll hit, and we'll watch a quick video on, is another one that's relatively fast in regards to our own timescale, but I thought it was kind of fun and interesting to look at. So in this one, we have mercury thiocyanate, and they put it in a terrarium just so that it looks kind of cute. And you'll see why in a minute. It's also relatively dangerous, so that's why the gloves. And with just a little bit of heat to get it started, and then the heat can actually go away and it will take care of itself, we start to get this Cthulhu-looking creature emerging. Of course, it's not really a creature. What's really happening is that the air is getting trapped inside the solid, and so it grows and grows and grows, making it look like a creature, though of course in actuality it's just a bunch of chemicals surrounding air. But this one also you can see is very fast. We can watch it happen. And not all chemical reactions are like that. A lot of the ones that you do in lab and things of that sort are also very quick and compared to our time scales because they have to be to get them done. And this will just keep growing for a while. You can YouTube it if you want to watch it again or watch more of it. So there's also, of course, reactions that are very slow in regards to our own time scale. Slow and fast and everything with kinetics is going to be a relative issue. So for instance, rusting is something that we know of, we know it exists, and we know it's a chemical reaction. You're turning a metal, a solid metal, into its ionic species through water and air. And so rusting is a really common one that we see, but there's another very, very similar reaction that turned the Statue of Liberty green. It of course wasn't always green. It was copper to begin with, still copper, just a different form of it, but it was coppered color originally. And then the water and air that reacted with it, and we'll learn about all of that when we do electrochemistry, turned the outside area of it green. And actually this ends up forming a bit of a protective seal around it because the water doesn't actually get to the copper to oxidize more of it. So we'll learn about those specific reactions later on, but it's just to give you an idea that some of them are very slow. So let's look at one more. And this is to kind of get at why we might need to look at kinetics more than just thermodynamics. So last quarter, you spent a lot of time on deciding if something would or wouldn't happen, whether it was spontaneous or not. Now, diamond and graphite are both carbon, both pretty much pure carbon, except for some impurities, but they're very, very different structures. So carbon, in terms of graphite, are just these carbon sheets that kind of align with each other. And that's why you can kind of flake it off when you go to write or whatever. Diamond, of course, is very, very different. It's a three-dimensional crystal structure like you see here. Everything is attached, and so it's very, very stable. However, if you actually look at the formation between graphite and carbon, it turns out that turning diamond into graphite has a negative delta G. Now think back to 1B and what you learned about negative delta Gs. It means it's spontaneous. So the question is, why aren't all of our diamond rings turning into graphite? Why are diamonds forever? Well, it's not, technically they aren't. They're just for a really, really, really long time. And so what happens here is we call it kinetically hindered. It takes so much energy to get it from one to another that it's happening so slowly that it's just not going to happen on any sort of time scale that we see or that we deal with. And so it's not so much that they're forever, but they're for so long that in our timeline it seems like forever. And this is a common thing that happens with reactions, where thermodynamics might tell us this is going to happen. But when we look at the reality of it, it doesn't happen. And that's a lot of times because of these kinetics. It's happening so slowly that we just don't see it happening. So throughout this chapter, we're going to be covering rates of reactions in slightly more scientific terms than we have here, which includes stoichiometric relationships and reaction orders. We'll be using data to determine rate laws. This is our most efficient and most common way of determining rate laws. And then we'll be using those data to determine the actual mechanisms behind reactions. And we'll actually be spending more of our time there looking at reaction mechanisms, comparing them to rate laws and seeing if they align. Just because actually determining reaction mechanisms goes a little bit above what this class covers. And then lastly, changing reaction rates. How can we speed these up or slow these down if we need to?